This is part of lesson 9.5, Vectors in the Plane. In this part of the lesson, we're going to talk about direction angles of a vector and use that to help us do a application problem, which is closely related to physics. The direction angle of a vector is the angle the vector makes with the positive x-axis. So if you write your vector v in component form, a comma b, then the a component form, or a component part, can be found by taking the magnitude of the vector times the cosine of the angle that the vector makes with the x-axis. And the b part of the component can be found by taking the magnitude of the vector times the sine that angle makes with the x-axis. And also, if you need to find the angle, you can find it by using the relationship that the tangent of theta is equal to b over a. So breaking this down into the picture we see right here, what you see is you have this vector v, and its magnitude is the length of the vector right here. So if we choose some point here and call that AB, then what we're going to find is our component A here can be found by taking A is going to be equal to the magnitude of V times the cosine of theta. And the reason for that is that cosine of theta is going to equal the adjacent side, which has length A, divided by the hypotenuse of this right triangle, which is V. And the same can be said for our B. So B can be found by taking the magnitude of the vector times the sine of theta. And again, that comes from the fact that sine of theta is going to be the opposite side, which length is B, divided by the hypotenuse, which is the magnitude of the vector. So using that, what we can do then is also write our vector in linear combinations. So it's listed here. V is going to equal, you can write it in component form, which is the magnitude of V times cosine theta sine theta, which is also the same as writing, instead of writing A, you're going, whoops, I thought I changed to the marker, I apologize. A times I, because you have magnitude of V cosine theta, I, plus magnitude of V sine theta, which is B, J. So you can write it either in component form or as a linear combination. All right, so example 7, we are to write the vector V as a linear combination of the unit vectors I and J if the magnitude of the vector is 4 and the angle measure is 30 degrees. So we have enough to write it as a linear combination. So what we're going to do is we're going to write that V is going to equal 4, the magnitude, times the cosine of 30 degrees. I, whoops, and then I write a J. I plus the magnitude 4 times the sine of 30 degrees, and then my J. So V is going to equal 4 times the square root of 3 over 2, I, plus 4 times 1/2, J. So simplifying, we get 2 times the square root of 3i plus 2j. All right. And then the last example is a really nice physics example. We have a weight of 500 pounds is suspended from a steel beam by 2 cables shown at right. What is the magnitude of the forces on the 2 cables? Now what you want to understand is if we are to draw a force diagram made up of vectors, we're going to have this. So I'll draw it over here. We are going to have first you have the weight of the 500 pounds pushing down this way. We'll call that F3. Okay, because the weight is sitting like right here. Okay? And then we have the weight of the two cables. So we have a weight that's pushing back this way, which is F1 with cable 1. And then we have, I won't make that so the angle's a little different. We have this angle here. This is my F2, which is a weight from the second cable. Okay, now we know this is an angle of 25 degrees, and the other one is an angle of 65 degrees. And so the angle in between them is, if you need it, it's 155 degrees, because that's 180 together. Okay, so we're going to write some equations for our forces, and then we're going to use that to solve a system of equations to find the actual values of the forces. So our three vectors are going to look like this. So F1 is going to be the magnitude of that vector. I'm going to call it little f1. And then it's going to be times the cosine of 65, comma, sine of 65. And then force 2 is going to be the magnitude of force 2 times the cosine of 25 degrees and the sine of 25 degrees. And then finally, force 3 is the easiest one to work with. Since it's completely vertical, there's no x component, and the force on it, and since it's in the negative direction, downward, it's going to be negative 500. So what we can do is we can write these as decimal equivalents and then write them out. What we want to remember is this idea that since the weight is suspended, it hasn't fallen, I'm in trouble writing the word suspended, the sum of the forces are balanced because if one force was more than the other, it wouldn't be still. It would be moving, either be falling or swinging to one side or something. We want to remember that we're going to have the resultant vector of 0, 0, and that's because F1 plus F2 plus F3 has to equal 0. So that's the equation we're going to work with that's going to help us out. So rewriting these vectors, as I said before, F1 is going to equal our little f1 times, and giving you the decimal equivalents of 65 for cosine and sine, I'm going to get 0.4226, comma 0.9063. F2 is going to be equal to a little f2 times, oh, I forgot the negative sign up here. I need that to be negative because based on my force diagram here, my F2 is going to have a negative x component because of where I have it located in my picture. The y is in the positive side of the coordinate plane, but the x is in the negative part. So I apologize, I missed that when I wrote the first part. Okay, so 0.9063, comma 0.4226. And there's nothing to rewrite for F3, so I'm not going to. So using this balanced equation, I'm going to write these out. So I'm going to have little f1 times 0.4226, comma 0.9063 plus little f2 times negative 0.9063, comma 0.4226, and then plus 0, negative 500, and of course that equals my resultant vector 0, 0. All right, so now breaking these up into their x and y components, I have two equations. I have two unknowns, little f1 and little f2. I can solve a system of equations to find those two forces. So that's what we're going to do. So our two equations are going to be (0.4226F1) minus 0.9063F2 is going to equal the x component of the resultant vector, which is 0. If I wanted to, I could even include a plus 0 here for this x part, but it's unnecessary. And then the other equation is going to be 0.9063F1 plus 0.4226F2, and then minus the 500 is going to equal 0. So this time I do need to include that force from F3 because it is all entirely in the y direction. Okay, so what I'm going to do is I'm going to take this first equation and I'm going to solve it for F2. So I'm not going to show all the steps. I'll just let you know that we get F2 equals 0.4226 over 0.9063 F1. I'm sure you guys will feel confident enough to simplify that, but if not, I can go over it in class tomorrow. So then I'm going to substitute that in for F2 in the second equation and rewrite it a little bit. So I have 0.9063 F1 plus 0.4226 times, and now I'm going to put that term in there, 0.4226 over 0.9063 F1, and this is now going to equal 500. And solving that, simplifying it, I get this. I'm going to have 1.10335 F1 is going to equal 500. So I get that F1 equals 453.165 foot-pounds. And then I can go back and substitute it in my fraction and get F2. So I'll have 0.4226 over 0.9063 times my 453.165. And I get that F2 is 211.306 foot-pounds. Okay, that's the end of the lesson. And again, if you have any questions, you can ask tomorrow in class, and I'll be glad to answer them.